In the previous video, I had done how to find the PDF of a random variable that is a function of two other random variables, given their PDFs. In this special case, where the functional relationship is just a sum of two random variables, and those random variables are independent, then there's a alternative way to do this. Let you figure out if you think it's easier. But first, let's look at what's the Fourier transform of a PDF, whatever it is, Z in this case. You might not remember it, but here's the Fourier transform of any function. You put it in this integral and multiply it by e to the minus j omega, whatever your variable is. Well, in terms of probability, what is this thing? If this f of z is a PDF, this is just the expected value of e to the minus j omega z. And in this case, z is a sum. So this z is x plus y. And remember, you could, if they're independent, you can break up an expectation like this. It's, well, this exponent, this exponential, because it's a sum, is a product. And because they're independent, the expectation of the product is the product of the expectations. And this is then the Fourier transform of x. This is the Fourier transform of y. So we have this relationship. The Fourier transform of the PDF we're looking for is this product of Fourier transforms of the two given PDFs. And a feature or relationship of the Fourier transform is if you have this relationship of their Fourier transforms, it translates into convolution in the good old function space. Not involving the Fourier transform. So we have these two things, whether you find it easier to do Fourier transforms or to do convolutions, you have a new way to find PDF. We don't have to necessarily do the convolution. We could find what the Fourier transform is by multiplying these Fourier transforms and then take its inverse Fourier transform. You can go through a similar derivation if your PDFs are zero for negative arguments. The same kind of derivation, you would use the Laplace transform. And again, the Laplace transform, product of Laplace transforms is a convolution in the time domain or the variable domain. Let's take an example. Now you're going to need a Fourier transform table to do this. Let's say the PDF of x and y in this case is this pulse, or it's just uniform from -1 to 1. So they both have the same Fourier transform. And we find this thing in the Fourier table, d, which was the Fourier transform of a pulse of extent d, symmetric pulse of extent d. Here, d is from -1 to 1, it's an extent of 2. So here's the Fourier transform of x, Fourier transforms of their PDFs. So that the Fourier transform of the result is that sinc squared. Now we need the Fourier transform table to find the inverse Fourier transform of this guy. And if you look in that table, you'll find this thing, which was the Fourier transform of a triangular pulse, if you want to call it. It kind of looks like this. We want our argument to be just 1, so we need d to be 4. So we get 2 sec squared of t equals 4. So our PDF is half of that inverse. So we get a rectangular, triangular pulse. Triangular pulse. It will look like this. So here's the PDF of both x and y. Here's the PDF of their sum. I'm not going to go through all of this one, but if you shifted that pulse, well, or a shifted pulse of width 1, yeah, they're each distributed from 0 to 1 in this case, instead of from -1 to 1, just from 0 to 1. The Laplace transform of each of them is this, so that their product of their Laplace transform is this. And then you have to take the inverse Laplace transform of this guy. And you need to know how to do that. I'm not going to go through this because it's a little bit too Laplace transform. So that's it. And that is not only the end of this video, it's the end of Module 1, my review of probability. Next subject is going to be random processing.